Section 10.3. Periodic lengths. One easy way to achieve variable length encryption is to use multiple substitution tables, one table for each desired block length. If these were blocks of letters, the substitution tables would quickly become enormous. Instead, we'll use bits. Let the message be represented as a bit string. The message is enciphered by dividing it into short blocks of bits and substituting a block of the same length using the substitution table for that length. The lengths of the blocks can be periodic using a repeating numeric key, or they can be produced by a random number generator. Let me demonstrate using a small example. There are 3 substitution tables for blocks of 2, 3, and 4 bits. In a practical cipher, I would use blocks of 3, 4, 5, and 6 bits, but you can go up to 16 bits, or possibly longer, if you had the storage. For this simple demonstration, I have used a standard alphabet, filling it out to 32 characters by taking symbols from the top row of the keyboard, going straight left to right. The 3 substitution tables are: here is a sample encipherment using the repeating key 3, 2, 2, 4, 2. This version, which I will call BitBlock SA for standard alphabet, has modest strength. There is one key for mixing each of the substitution tables and one additional key for the sequence of block sizes. When there are just a few substitution tables, the block sizes are all small, and the sequence of block sizes is small. BitBlock SA is rated 3. Otherwise, it is rated 4. One way to strengthen this cipher is to use well-mixed keyed alphabets for converting the letters to bits and the resulting bits back to letters. Let's call the mixed alphabet version BitBlock MA. It is rated 7. Section 10.4. Huffman substitution. Section 4.2 describes how you can use Huffman codes for text compression. Huffman substitution is a way that you can use Huffman codes for encryption. Huffman substitution uses 2 sets of codes. The codes from the second set are substituted for the codes in the first set. These might be the same set of codes, but in different orders. The message is represented as a string of bits, for example by using one of the standard computer representations such as UTF-8 or Unicode. This bit string is separated into a string of codes from the first set of Huffman codes. Then these codes are replaced by codes from the second set. Huffman substitution does not compress the message, although the length of the message, measured in bits, can change if the codes in the first set have different lengths from their substitutes in the second set. Recall that a set of Huffman codes must have a prefix property. That is, no Huffman code in a set can begin with another Huffman code from the same set. For instance, you could not have both 1101 and 11011, because if the string you are decoding started with 11011, you would not know whether the first code had 4 bits or 5 bits. With the prefix property, there is no need to have a separator between the codes, the way that Morse code groups need to be separated. Let's look at how to construct a set of Huffman codes with the prefix property. Begin by listing the single bits in either order, namely 01 or 10. For example, for each item on this list, either accept it as a complete code or extend it to make 2 longer codes by appending a 0 to one copy and a 1 to the other copy, again in either order. For example, we could accept the code 1 as complete and extend the code 0 to make 2 codes, 00 and 01, like this. This process can be repeated as often as desired. For example, we could accept the code 01 as a complete, but extend the code 00 one more step to make codes 000 and 001. This process can be continued until you have the desired number of codes or the desired range of code lengths. However, 4 codes are enough for this example. We will accept both 000 and 001 as complete codes, making a complete set of 4 codes. We can estimate how long the average code will be when we encipher a bit string using these codes. There is a 1 in 2 chance that the string will begin with 1, thus a 1 in 2 chance that the code will be 1 bit long. There is a 1 in 8 chance that the string will begin with 000, and a 1 in 8 chance that it will begin with 001. In either case, the code would be 3 bits long. There is a 1 in 4 chance that the string will begin with 01 and the code will be 2 bits long. This is a complete set of codes, so there are no other possibilities. Combining them gives the expected code length 1/2 plus 3/8 plus 3/8 plus 2/4 equals 14/8 equals 1.75 bits. After the first code has been substituted, the probabilities are the same for the next code, so the expected length of all codes is 1.75 bits. This is less than the average length of the codes, which is 2.25 bits. Here is an example of Huffman substitution. There are 2 sets of Huffman codes. The codes in the left column are replaced by the codes in the right column. Both sets of codes have the prefix property. The plain text is Liberty, encoded with the standard 5-bit representation. A equals 00000, B equals 0000001, C equals 00010, Z equals 11001. The first line of 5-bit groups is the word Liberty encoded in the standard way. A equals 00000, B equals 00001, and so on. The second line of binary is the same string of bits, but divided into Huffman codes from set 1. The underlined digit 1 is padding that was needed to fill out the last Huffman code. The third line of binary replaces each code from set 1 with the corresponding code from set 2, that is, the third line is the result of the substitution step. The fourth line of binary is the same bit string as the third line, but divided into groups of 5 bits. Notice that line 4 is 4 bits longer than line 1. The final line is the ciphertext using the same standard 5-bit representation for the alphabet. The last letter of the ciphertext could be either I or J, since the last binary group has only 4 bits. If you are doing this by computer, it is not necessary to compare the front end of the bit string to each of the Huffman codes in turn. Suppose that the longest code has 6 bits. You can make up a table of all 64 possible 6-bit combinations. Each entry in the table will tell you the length of the code in bits and give its substitute. Each time you perform a substitution, you use the first 6 bits of the string to look directly in the table. Suppose, for example, that the first Huffman code is 00000 and its substitute is 0110. The possible values for the first 6 bits of a string starting with that code are 000000 and 000001. So entries 000000 and 000001 in the table would both give the code length as 5, and the substitute for that code as 0110. To perform the substitution, you would delete the first 5 bits of the string and append 0110 to the result string.